Today we're going to talk about video 4.3, Riemann sums and definite integrals. The first part of it is going to be Riemann sums, and I have a worksheet for you. The second part is definite integrals, where you'll get to see some examples. All right, let f be defined in a closed interval ab, and let this little delta be a partition of ab such that a, b, it's in order. That means it's ordered. Here, x of 0 is less than x of 1, less than x of 2, stuff like that. Where these delta x of i's is the length of each ith subinterval, basically the length of the rectangles, okay? Length being this way on the x-axis. If c of I is any point in the subinterval, then what we're going to do is we're going to sum up the function at each of these rectangles and multiply it by the width of the rectangles. That's what this says right here. We're going to take the function of the rectangles, or where the height is, and multiply it by the width. Height, width, add them up. This is called a Riemann sum. And it would be nice of this partition, whatever this partition is. Now, if we take all these rectangles and we send it to 0, if we take their width, we send them to 0, we're going to get really, really close to, this means norm of the interval, like the normal value. I really don't know. You don't really need to know this, but the delta x's, so we're taking the limit, and I'm going to change this just of delta x, and taking these all going to 0. So you're taking the width of the rectangle, and now we're sending the width, and it's getting closer and closer to 0. We're going to get the area underneath the curve, the exact area underneath the curve, not the approximate, where we are approximating left endpoint, right endpoint. And this is called the definite integral. And let's talk about this definite integral. You've seen integrals before. However, now they have two numbers here. They have an a and a b. A is your lower bound, or lower limit of integration, and b is your upper limit of integration. It's called the definite integral because you're going to get an answer. Anytime there's numbers here, you're going to get a number answer. Area is a number, all right, and some square units. So the number of rectangles are going to infinity, or we're taking these going to 0. These going to 0, number of them going to infinity. All right, so we'll get a worksheet on that later. I'll show you a couple of AP problems, but I'd like to really focus on this, because this is our definite integral. By the way, both are very important, the Riemann sum and the definite integral. So, a couple of things I should say before we start. There's a theorem that says if it's continuity will imply we have integrability. Did you hear that? Integrability. That means you're able to integrate if it's continuous. And this area is on this closed interval. This is A to B, it's a closed interval. And when you're graphing these things, area above the x-axis is positive, area below the x-axis is negative, and area or lines on the x-axis, they could be 0, because you could have them equal out on top and bottom. So when you're talking about area, we're going to do it of figures first, and then we're going to go into doing the integral, which is our antiderivative. All right, we're going to do a couple of problems here. And here's my first example. And I say, look at geometric formulas to evaluate. I want the integral from 1 to 3 of 4x. Well, what I can do is I can take a graph. 4x is this, 0, and it goes on, okay, but we want it from 1 to 4. And this is f of x equals 4x, okay? So that's 1 and that's 4. If I think about the area of this figure, okay, it's actually going to be a trapezoid. And if you remember the trapezoid, it's the average of the bases times the height. Well, the height is here. The height is here. The height is 4, okay? Or I should say 1 to 3, because I don't even know how to read numbers. My bad. 1 to 3, the height is 2. So the height is 2, and the average of the bases, well, this is B1 here. This is B1. This is B2. So the base at 1, when I plug it in, is 4. The base at 3, when I plug it in, is 12. So it's 4 plus 12 divided by 2. 4 plus 12 divided by 2 is 16, divided by 2 is 8. 8 times 2 is 16 is our area of the first one. That's how it's done, folks. All right? These, remember to find these red lines. I plugged it into the function. That's it. Next one. We have x plus 2. X plus 2 is here. This is 2. It's a line that has y-intercept is 2. And I'm going from 0 to 3. So we're given another trapezoid. Oh yeah, another trapezoid. So this trapezoid has a 0 to 3 is 3. 3 is our height. Average of the bases. We have 2 here, plus, put 3 into the function, 5 divided by 2. The average of the bases is 7 halves times 3, that's 21 halves. So that is the area. That is these are the answers. 16, 21 halves, or 10 and a half, if you will. All right, now look at this one. This figure is going to look like a semicircle. It's going to go from -2 to 2. All right, and it's that semicircle right here. Because it's the square root. The plus square root's on top, minus the square root's on the bottom. So if I remember, this is pi r squared. The r is 2. But actually, it's over 2 because it's a semicircle. So it's pi times 2 squared over 2. And I'm going to get 2 pi. So that's the area of this guy. The area of this guy is 2 pi. So we're doing it by, right now, we're doing it by graphing. Next video, you'll see how to do it analytically, algebraically. There's some special definitions. If I'm going from A to A, that means I'm not even spanning anywhere. So the area is 0. It's like from here to here. From here to here, nothing. If I go from A to B, it's the minus of A to B. So I could switch these limits of integration, but you just got to remember that it's the negative of that. And then there's some properties to note. Here's some properties. I could pick somewhere in between if it's continuous and add them. Makes sense? If I'm going from A to B, I could pick some C in between and add them up. All right, C might be the place where it's maybe discontinuous, so I'd have to break it up. I can go A to B. I can bring constants outside, like this one, and the sum of the integrals is the integral of the sums. Okay, so you can take the integral of this plus this, or you can break it up. So far, so good. Okay, this is actually my last problem. Quick video today. We're going to set up the definite integral and solve using geometric formula, 2 minus x. Okay, and I want to go from, let's go from 0 to 3. I have to tell you this. This would be given in the problem. From 0 to 3. All right? So now let's graph this baby. Here we go. Here's 2. It's negative slope. So 2, 2, 3, like that. So I'm looking at this area, the blue area, and I'm also looking at the red area. And this is going from 0 to 3. Okay? I'll put that, I don't like where I put that 3. I'll put that 3 over there. Nice, nice. Nice, nice. All right, so we got 0 to 3. This is a problem where we're going to use one of those properties because we're going to break it up. Where does it hit the x-axis? Hits the x-axis at 2. So I really want to do this. I want to take from 0 to 2 of 2 minus x, okay, dx. And I want to add to that, 2 to 3. 2 minus x dx. So these are triangles. Oh yeah. These are triangles. Triangles are 1/2 base times height. So this is 2. This is 2. So the area of that triangle is 2. 1/2 base times height. This is a triangle too. This is 1. And how high does it go? I believe it goes, actually, it goes -1. So it's going to be -1/2. Or 1/2, and since it's below the x-axis, it would be -1/2. So the answer to this is 1.5. All right, once again, this was 1 and 1, or put 1 here. But since it's negative or on the bottom, that's why it's -1. I always do that -1 thing to make sure that I know I'm going down, so I'll get the negative area no matter what. All right, so you get 1.5. That's our area of this figure. All right. Anybody have any questions? All right, for homework tonight, what I want you to do is I want you to do page 278, 14 to 32 even. That's going to be practice with all the area type problems. Tomorrow in class, we'll do a little bit more area, and we'll do some Riemann sum problems together. Okay? Enjoy your day.